Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss idea of singularity, pole and residues. Let's begin. Singularity of an analytic function. If a function f of z is not analytic at a point A within that of a given region, then the point A is said to be singular point of that given analytic function. Singular point, or we can say it as singularity of the given function. Let me take an example. A function f of z is given as 1 divided by z minus 2. That function is analytic except at point z is equal to 2. So here taking z minus 2 is equal to 0, we have z is equal to 2. Therefore, at z is equal to 2, the function is not analytic. And f of z tends to infinity when I put z is equal to 2. And also its first order differentiation is at infinity. Therefore, that given function f of z is equal to 1 divided by z minus 2, that point z is equal to 2 is said to be as the singular point. So, the singular point of f of z is equal to 1 divided by z minus 2 is 2. That is the singular point of that given function. Types of singular point. Isolated singular point. As the name indicate, it is isolated. If z is equal to a is a singularity of that given function and there is no other singularity within a small circle surrounding that given point z is equal to a, then that given point is said to be an isolated singularity of that given function. Example, as f of z is given as 1 divided by z minus 2 z minus 3. So, it has two singular points as z minus 2 z minus 3 is equal to 0. We have z is equal to 2 3. So, it has two singular points. And these two singular points are isolated. It has two isolated singular points. Next, non-isolated singular point. If that singular point is not isolated, then it is said to be non-isolated singular point. Let me confirm it by taking an example. If a function f of z is given as 1 divided by sin pi by z. That given function is not analytic at all points where sin pi by z is equal to 0. Sin pi by z is equal to 0. That is, at points pi by z is equal to n pi. Since sin pi by z is equal to 0, so pi by z is equal to n pi, which implies pi is equal to 1 by n, whereas the values of n from 1 to 3 up to continued. Thus, z is equal to 1, 1 by 2, 1 by 3, dot dot dot. Here z is equal to 0 are the point of singularity. Z is equal to 0 are the point of singularity. So z is equal to 0 is the non-isolated singularity of that given function. Therefore, z is equal to 0 is the non-isolated singularity of the function 1 by sin pi by z, because in the neighborhood of other singularity, that are the other singularity. So the neighborhood of other singularity z is equal to 1 by n, by putting the values of n. Since n is large, where n is very large, that's why the singularity is said to be non-isolated singular point. Z is equal to 0 is the non-isolated singularity of that given function. In this way, we categorize the singular points as isolated singular point, or which is not isolated are said to be non-isolated singular points. By taking an example, we clarify how we say it as either isolated or non-isolated. Next, pole of order m. If a point z is equal to a is said to be pole of order m of that given function f of z. For that, it is the condition if the limit z tends to a, z minus a to the power n f of z is exist and finite, then we say z is equal to a is the pole of order m. We understand it very clearly by taking an example. The given function f of z is given as z divided by z minus 2, z minus 3 to the power 2. So it has two singular points at 2 and 3. It has singular points 2 and 3, which is z is equal to 2 and 3. That singular point is said to be the pole, but what order of that pole? To find out the order of that given pole, we have therefore taking limit z tends to 2, z tends to 2, z minus 2 of that given function f of z, and z is equal to 2. First we put by that given formula to evaluate the order of the pole, which is equal to limit z tends to 2, z minus 2, 2 divided by z minus 2, z minus 3 square, that is the z. Z minus 2 cancel out. Now evaluating the limit, that is 2 divided by 2 minus 3 square is equal to 2, which is finite and exists. Therefore z is equal to 2 is the pole of order what? Order 1. Similarly, we can take the limit by taking z tends to 3. Similarly, z is equal to 3 is another singular point, that is the pole of order what? 2, that is z minus 3 square, that is the pole of order 2. In this way, the pole of order is calculated. First we have to prefer that limit is finite and exists. If that limit is finite and exists, then we say that is the pole of that given order. By taking an example, we clarify. At the singular points, we calculate the pole of that order. It has two singular points, 2 and 3. So 2 is the pole of order 1, 3 is the pole of order 2. In this way, we have to analyze the singularity of an analytic function, singular point which is said to be the singularity of the given function. Taking an example, we will clarify. Next, types of singularity as isolated singular point. Its example, the singular points which are not isolated, we say it has the non-isolated singular points. Taking an example, it understood what is non-isolated singular points. Next, pole of order m. By taking an example, we clearly understood what is the pole of order m. Next, idea of residue. If f of z has an isolated singular point at given point, that is z is equal to a, then the coefficient of z minus a to the power minus 1 in the Lorentz series expansion of that given function f of z about that point a is called the residue of f of z. We expand Lorentz series for what condition? When that given function is not analytic within that of circle, then we expand that function by using Lorentz series expansion. In Lorentz series expansion, here we take from Lorentz series expansion, Lorentz series expansion, the given function f of z is expanded about that point a as a naught plus a1 z minus a plus a2 z minus a square plus dot 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 again b1 divided by z minus a plus b2 divided by z minus a square plus dot dot dot. What is residue? Residues is the coefficient of z minus a to the power minus 1. Here z minus a to the power 1, when it transform to that of numerator side, it will be z minus a to the power minus 1. The coefficient of z minus a to the power minus 1 is equal to b1. So it is found that the coefficient of z minus a to the power minus 1 in above series is b1, that is b1 is the residues at z is equal to a of that given function f of z. So residues is evaluated at the pole. There are various techniques. By using these technical rules, we can easily find out the residues. So the working rule for residue. Working rule for residue at simple pole. At simple pole having the pole of order 1. The residues is calculated as residues at A is calculated by taking limit z tends to a, z minus a to f of z. Next, at pole of order m, so residues at A calculated as 1 divided by m minus 1 factorial limit z tends to a derivative of m minus 1/3 with respect to z of m minus 1/3 z minus a to the power m of that given function f of z. Again residue at infinity. Residue at infinity. Residues at infinity is calculated like that of limit z tends to at infinity minus z f of z. Now we use an example to understood how to evaluate residues of a given function at pole. Example: find the residue at pole if the given function f of z is equal to 1 divided by z minus 1, z minus 2 to the power 4th. Look at that given function. It has two singular points, one is 1, another one is 2, but one pole of order 1, here 2 is the pole of order 4. It is clearly visible from that of function. Here f of z is equal to 1 divided by z minus 1, z minus 2, here z minus 2 to the power 4. It has z is equal to 1, which one is simple pole, and z is equal to 2, that is the multiple pole of order 4. By using the formula or simple pole and pole of order m, we can easily evaluate the residues of these given points. Therefore, first residues at 1, the formula is limit z tends to 1, z minus 1 of that given function f of z. That formula is used, which is equal to limit z tends to 1, z minus 1 f of z, 1 divided by z minus 1, z minus 2 to the power 4, z minus 1 cancel out. Now we can evaluate the limit as z tends to 1, putting the value, we have 1 divided by 1 minus 2 to the power 4th, which results 1. So residues at 1 is equal to 1. Next, residues at 2, it has the multiple pole of order 4. That formula is used. According to that formula, residues at 2 is calculated 1 divided by 4 minus 1 factorial limit z tends to 2 with order m minus 1, here m is equal to 4, 4 minus 1, that is 3, d z 3, z minus 2 to the power 4th f of z, that is equal to 1 divided by 3 factorial limit z tends to 2 dz cube z minus 2 to the power 4th f of z, 1 divided by z minus 1, z minus 4, sorry, z minus 2 to the power 4th, z minus 2 to the power 4, z minus 2 to the power 4 cancel out, 3 factorial, that is 6, limit z tends to 2 d cube dz cube 1 divided by z minus 1. Its third order differentiation 1 by 6 limit z tends to 2. Its third order differentiation is minus 6 divided by z minus 1 to the power 4. First differentiating with respect to z, again differentiating with respect to z, and again differentiating with respect to z. Then we have the result minus 6 divided by z minus 1 to the power 4th. Now we can evaluate the limit by putting z is equal to 2. Here 6 cancel out, as that 6 is constant that to that of outside. So limit z tends to 2 minus 1 divided by z minus 1 to the power fourth. Here minus 1 divided by 1 to the power fourth results minus 1. Therefore, we have residues at 1 is equal to 1 and residues at 2 is equal to 2. Therefore, we have residues at 1 is equal to 1 and residues at 2 is equal to minus 1. So, residues at pole is evaluated for that of given function. It has two singular points as 1 and 2. One is simple pole, that one is multiple pole of order 4. By taking the formula to evaluate the residues at poles, by taking the corresponding formulae and we evaluate the correct result. So, with the help of this video lecture, we understand the concept of singularity of analytic function, singular point, types of singular point, isolated singular point, non-isolated singular points, and some examples: pole of order m, idea towards a residue, working rule for calculating residue for simple pole, pole of order m, residue at infinity, an example related to calculating residues. So, with this useful and informative notes, let me wind up this session. Thank you.